The right size on the line. Fantastic! Oh, that's actually a great bit.
So I appreciated the presentation and the discussion. Some of you had some experience with multivariate methods, and others just don't know what to say. What I'm going to do is at least give you an introduction to some of the methods, and those of you that are familiar with them, I'll just sit back and see if I do a good job or not, and the rest of you maybe get you over the first hump and give you a little bit of intuition for how some of the most commonly used methods actually work. So here goes. So the point was also made earlier. Data are usually multivariate. Why? Because when we carry out a study, we want to measure all kinds of things. We don't want to miss anything. And then that means we immediately face a challenge: how to work with such a complicated data set, such a big data set. So are there ways to find important patterns, if they're there, and not discover false patterns and so on, and allow us to move forward? So one of the things that we usually want is what we call ordination. And that means taking your observations and arranging them along some gradient or plotting them against some combination of variables that allows you to just look at this and go, oh, there's two groups, maybe. So you want to be able to visualize that complicated data set in a small number of dimensions, and then maybe find some meaningful combinations, like whatever combination of variables produced axis 1. Maybe you could use that in subsequent analysis. Maybe it has a ready interpretation. That can't be guaranteed always. The multivariate methods are used for ordination, as I said, and then also for a couple of other things. Classification, which is to place data points into groups, and then model fittings, some of which we've already dealt with previously, like stepwise regression. I'm not going to talk about that, and I'll talk a little bit about these two objectives: ordination and classification. Mostly ordination. And I'm going to start with principal components analysis. A, because it's pretty common. B, you've all heard about it. Maybe some of you haven't done it before. And C, because actually principal components does nothing at all. So it might be easier to intuit than anything. So I thought I would take an example from some measurements that I had handy on the computer, just looking at variation in beaks and bodies of Galapagos finches. We know that this is related to their different diets, and we would like to find out some way of ordinating these things to give us an idea of which species is close, which resembles other species, and which species are different from one another. So here's my data set, which was 14 species of Galapagos finch, averaged across populations, and then 5 different traits. Wing length, tarsus is basically leg length, the length of the beak, the depth of the beak, the vertical dimension, and the width of the beak. So how to illustrate this? Well, we only have 5 variables here, but already it's a challenge to visualize them. But this is one way: just plot all pairwise scatter plots. And it's kind of a good thing to do anyway, because you'll learn something useful. We've already used the command pairs, I think, in a previous workshop. So you can see immediately that most traits are correlated with other traits, and that the depth and the width of the beak are pretty much the same trait. The correlation is so strong between them. So we can start to see some of the patterns here. But it's a little bit hard in this space to figure out, which species are similar to which other species. And the problem of visualizing multivariate data, has been addressed by a number of people. This guy Chernoff came up with this method, which is referred to as Chernoff faces, and you can do this in R. The idea is that we're incredibly good at detecting differences between faces. Like I can tell you all apart. And so why not, millions of years of evolution have made this possible. And so take advantage of this, the fact that half our brain is pretty much wired to do just this. And that make each variation in one variable, a variation in a different trait of a face, so that we can see which species are relatively similar to one another and which ones are relatively different. Like this one's pretty different. You can see this right away. Well, it hasn't really caught on, okay? this particular method, but it's kind of fun to think about. Perhaps there are situations where it might be useful. Principal component analysis is one way in which as many as 5 or more variables might be used to display data points in a smaller number of dimensions. And so principal components analysis is commonly used to do this. And I did this for the Galapagos finches, and this is what it looked like. First principal component axis, second principal component axis. And the idea is that even though we're actually looking at 5 dimensions of data, and we've reduced it down to 2 dimensions, that the distances between points are approximately preserved. So points that are far apart, species that are far apart morphologically, well, they're going to be far apart in this space. Species that are closely resembling one another will tend to be close together. And so this is telling us something about the different phenotypes, the different beaks and bodies of Galapagos finches. And in this case also, even though the axes are composite variables, they have, in this example, a ready interpretation. So principal component 1 turns out to distinguish species on the one hand that have sort of thin, short beaks from individuals in species at the other extreme, which tend to be much larger. And so this first axis can be interpretable as sort of overall beak size. All of the beak dimensions separate those whose beak dimensions are large over on that side with those whose beak dimensions are small on this side. And in this case, the second axis is also relatively interpretable. Generally, it separates those species at one extreme that have relatively long bills for a given size from those that have relatively short bills for a given size. So would represent what we would think of as an axis of beak shape. So we're getting something interpretable from this analysis. So where did it come from? How did I get this? Is there any way beyond what I've just shown you to intuit something about the variation among the species and how they are arranged in this 2 dimensions? So principal component analysis is really pretty simple. You have a scatter of points and you turn it in order to visualize it from one perspective or another. And that's really all it does. So to illustrate this, I'm going to pretend that actually instead of 5 traits, we just measured 2. And I'm going to do a principal component analysis just based on 2 traits. Which kind of, well, it doesn't make a lot of sense to do that, other than it will help to illustrate how the method actually works. So the 2 traits that I've chosen are the length and the depth of the beak, and here are the 14 species. You can see there's some correlation between these 2 traits across the different species. And what I want to do is a principal component analysis of these 2 beak traits. There's always just, so if there are 2 traits, there are 2 principal components. If there are 5 traits, there are 5 principal components. Nothing has changed in that regard. What principal component does is it basically takes a scatter of points, which can be visualized in 2 dimensions here, and turns them, rotates them in such a way that we can better look at it. In the case of 2 dimensions, you can draw an ellipse around these 14 species. The first principal component is basically just the long axis of that ellipse. So that's what is meant by the most variable direction. And the second most variable direction in the case of 2 dimensions is the only dimension left, which is the one that's perpendicular to it here. And so to do a principal component analysis in 2 dimensions involves basically drawing that line, flipping it, and plotting it. And nothing else has changed. The new axes are uncorrelated. But because all I've done is turn things, the distances between pairs of species are completely unchanged. Now the distances might start to change if you start with 5 dimensions, reduce it to 2, and then throw the other 3 dimensions away. Well, there's usually little reason to do that. So that's it. That's principal component analysis. But there's a whole sort of terminology involved in doing a principal component analysis, and I'm going to try and interpret it for you so that you can recognize the process of just rotating things and looking at them from a different perspective, and the quantities that sort of get spit out in R as a principal component analysis. So here's a little bit about what goes on behind the scenes. So how principal component analysis works is it has some, you start with some matrix that summarizes the relationships between the data points that are in your analysis. And one way to do this is to use the covariance matrix, which is something that we've uncovered before. And so if we have just 2 traits, x1 and x2, we have a 2 by 2 matrix here where along the diagonal of this matrix is the variance in x1, the variance in trait x2, and then the covariance is off the diagonal. And so here are the numbers for the 2 finch species in these 2 traits. So the variance in beak length among the species, the variance in beak depth among the species, and then the covariance between the 2. The covariance is the numerator of the correlation. So it's part of calculating the correlation, but the correlation standardizes it so that it stays between -1 and 1, but the covariance is just an unstandardized version of a correlation. Then, on the process of rotating this and producing the principal axes creates new variables that are called principal component 1 and principal component 2. And as part of this rotation, the correlation, these new axes are uncorrelated. So there's zeros on the off diagonal. There's no covariance between PC1 and PC2. And what's along the diagonal is the variance of the measurements in this first axis, and the variance in the measurements along the second axis. And just to keep things complicated, these variances are called eigenvalues. So you've probably heard about eigenvalues, and that's all they are. It's just the variances of those new axes. And just again to prove to you that nothing has changed, the sum of this variance plus this variance is exactly the same as the sum of the variances of the original traits. So all we've done is turned them in such a way that PC1 is the most variable direction, the long axis of the ellipse. And then PC2, in the case of 2 dimensions, is just the dimension that remains. That's perpendicular to it.
So wait, Dolph, you're saying that, so PC1, that number is 0.192. The numbers, so the slide beforehand, those numbers would sum up to that number?
That's correct, yeah. So those 2 numbers would add up to the same as 0.0518 plus 0.1741.
Okay.
Well, how did I do this transformation? How did I calculate these new axes? And these are the transformations that basically converted this to this. So to calculate the first principal axis, I took 0.413 times Kalman length, beak length, plus 0.911 times beak depth, and that's PC1. It's just a linear combination of the original variable. And this is the linear combination for PC2. So minus 0.91 times column length plus 0.413. That's peak depth, and that's how I got the position of every species on the second dimension. So these columns of numbers, just to keep things complicated, are called eigenvectors. You've probably heard what they are, but they're nothing more than the column of numbers that converts the original traits into the PC.
Who was Eigen?
Who is Eigen?
Yeah.
I think Eigen is from a German language. I think it means unique in German, or an individual, or one. So that's what those numbers are. And these numbers also allow you to provide an interpretation for these axes as well. So I look at this number and I go, oh, this axis here is separating those individuals that have sort of long and deep beaks from those species that have short and narrow beaks. And I can say that because both of these dimensions load positively onto PC1. But the second eigenvector separates those individuals that have deep and short beaks from those individuals that have narrow and long beaks. So by virtue of the fact that it includes both positive and negative numbers means that it's a shape trait. It's changing along the second axis. Beak depth is increasing while column length, beak length, is decreasing. And so in this case, there's a reasonable biological interpretation of the second axis as well. So I didn't go into this analysis saying, oh, what I would like is a beak size axis and a beak shape axis. And so, in large part, when you carry out one of these analyses, you cross your fingers and hope that when it's done, you look at the vectors and go, oh, I can interpret that. That makes sense. I'm going to call this one size. I'm going to call this one shape.
So wait, could you just do that one more time for explaining just the eigenvector 1 and eigenvector 2? Like those numbers, yeah, what those mean?
Yeah, so by virtue of the fact that these are both positive means that variation along the principal axis 1 is a simultaneous increase in both of those traits.
Okay.
At one extreme, and therefore a simultaneous reduction in those same two traits at the other extreme. But eigenvector 2 doesn't involve a simultaneous increase in both traits. An increase in one trait is accompanied by a decrease in the other. And so we say that that represents shape. So that would be the biological interpretation.
And so eigenvector 1 is showing that first figure, and eigenvector 2 is
right.
showing that.
And then the second one is shown.
Okay.
So these eigenvector numbers, the columns of numbers, they're called loadings, because they basically indicate the contribution of each of the variables to each of the principal components. So as you see, there's just a whole jargon associated with principal component analysis. But it's really quite easy, because nothing actually happened. All we did was turn things around so that we could look at them from a different perspective. And then say things like, most of the variation in the Galapagos finches is in beak size. Now, can we do this in 3 dimensions? Yes, we can. So it's still possible with 3 traits to visualize them, because the world's made up of 3 dimensions. And so here's a cluster of points, just an example that I found on the web. And it's spinning so that you can kind of see what the arrangement of points actually looks like. And so you imagine, hovering in the middle of this room, a scatter of points. Maybe it's in the shape roughly of a football or something like that. PC1 would be again, the long axis of that ellipsoid. And PC2 would then be the, you turn the football and find out where it's not going to be exactly spherical in circumference. So you'd find one dimension is a little flatter. That would be the second axis. That would be PC2. And then PC3 would be the last axis that remains that's perpendicular. So there's PC1, the red arrow. And then PC2 is the green arrow. And then PC3 is the blue one. So it's possible to draw them on a three-dimensional scatter of points in the same way that I was able to do it on that two-dimensional ellipse. But it gets hard to visualize as soon as you get above 3. And already I find three-dimensional graphs to be really difficult to interpret if they're stationary. So in the graphics lecture at the beginning of the course I talked about movies as graphs. And it's a reasonably good way of plotting data in 3 dimensions. So the idea is the same with 5 dimensions. I can always take any number of dimensions and reduce them to 2, but now I am missing something. I've turned it and I'm looking at it from a particular perspective, but I know that there's additional variation, for example, coming out of me from the page, so we don't see all of the variation. But nevertheless, if the 2 axes account for much of the variation, if the sums of the eigenvalues of the first 2 axes is a reasonably large proportion of the sum of them all, then we'll get a good idea from looking at this, looking at all the data in 2 dimensions. And that's kind of what ordination does. It's the eigenvalues that tell you how much of the total variation is captured by these components, and this is, I think, called screed plot. And here you can see that by far most of the variation in the Galapagos finch species is in overall size of the beaks. And then beak shape is picks up some of the rest, but by the time you get to components 4 and 5, there's not actually that much variation left. So even though you've measured 5 traits, and there are 5 dimensions, there's hardly any variation in at least 1 and possibly 2 of those dimensions. And this is what makes it possible to visualize, therefore, the data in a smaller number of dimensions and have it make sense. And here are the eigenvectors for the 5 principal components for the 5 traits. And so for PC1, all of these numbers have the same sign. And maybe except this one, which is Tarsus length. And this one contributes not so much as well, they're relatively small, but these 3 vary in the same direction. They have the same sign, and they're all sort of not 0, so basically PC1 is beak size. Wing length of Tarsus contributes somewhat, but not as much as beak. And PC2, again in this case, is shape. So especially the length relative to the depth of the beak. Whereas these other dimensions these other measurements don't contribute very much. It's mostly beak shape, length and depth. PC3 it starts to get harder to interpret. There's not much variation left in PC3, but it's mostly Tarsus length. And Tarsus length doesn't seem very strongly correlated with any of the other variables. So it sort of pops out as strong on one of the later PCs. And it does get harder and harder the more dimensions you try to include in your analysis. I was involved in a study of shape, a QTL analysis of shape variation in stickleback. And the reviewers said, we did all of the individual traits one at a time and came up with our results. And one of the reviewers said, we really need to, because these traits covary, we should do principal component analysis and genetically map principal components. We just thought, okay, let's just try this and see if anything makes sense. And we did the analysis and nothing really made sense. Principal component 17 had a very strong, genetic signal on one of the chromosomes, but I had no idea what that means. So we shunted it to an appendix and sent it back in. So that was 5 traits. Now what I want to show you is maybe the other extreme. This was a principal component analysis of nearly 200,000 traits. And what it is a sample of 1,387 humans from Europe. And each of those individuals was genotyped at 197,146 markers across the genome. So the data are loci, they're single nucleotide polymorphisms. And at every locus there are 3 genotypes then. Big A, little a, and then the heterozygote. And you can score those as 0, 1, or 2. Basically, what the measurement is at each nucleotide is the number of little a alleles. So those are the traits. And there's many, many, many of them. And so to factor the covariance matrix, which is 200,000 rows and 200,000 columns, but there are computational methods for doing this relatively efficiently in R. And so what these authors did was they ran all of these data through principal component analysis and then plotted them in 2 dimensions. And here they are. So PC1 is here, PC2 is there, and the individuals are coded by the color coded by the country that they lived in. So all the light greens are individuals that live in a country. The reds are another country, and so on. There are probably more than one shade of red here, so we'll start running out of shades of color. But the key thing from this graph is that we're getting some information even with 200,000 dimensions reduced to 2. We're seeing that people that live close to one another are actually nearby in these 2 dimensions. They tend to inhabit the same country. So there's a lot of signal in these 2 principal axes. And the big circles, by the way, I forgot to mention, are the country means. So these axes actually largely separate individuals that live in different countries in Europe. So points that are close together, they tend to be in the same country, and points that are far apart, they tend to live in different countries. So it's amazing how such a drastic reduction in the number of dimensions produces something relatively sensible. And why is it the case that nearby points refer to that individuals that live in the same country tend to be nearby on this space? And the answer is that, well, actually, people live in the same country genetically more similar to one another because they're more closely related if you looked at the entire genealogy of Europe. And so there's much more gene flow between populations in close proximity than there is between populations that are far apart, and that is reflected in the amount of divergence we see in these polymorphisms across the genome. Now, I've got one more plot, because what I've done is I've actually rotated this in order to show you one more thing, and that is Europe. So not only are nearby points, not only do individuals that are nearby on this plot in the same country, but individuals that are in neighboring countries are next, most distant on this plot. And geography determines how much gene flow there is. More between Spain and France than between Spain and Italy, and so the Spain and Italy are further apart than is Spain and France. So it's an amazing amount of information.
Would an outlier like Slovakia below Italy, would that be due to sample size potentially, or would that be just an artifact of the data?
Oh yeah, Slovakia falls out in the middle of the Mediterranean, but it's actually yeah, it's a very good question. There's something different about the people of Slovakia. And that may have something to do with the migration of peoples at one stage in the history. And also, I think that might also be reflected in like the language families. I don't know what Slovakian is, but it's probably not an Indo-European. Is it Indo-European?
It's a Slavic language.
What's that?
It's related to Russian.
Right, exactly. So it does have a somewhat different origin, and so there's probably been less gene flow between Slovakia and Italy than you might expect from their geographical proximity over history. Anyway, this is an amazing graph.
Why did they even think of doing that? Like, they thought maybe if they turn it on those axes, it'll look like Europe.
Well, they had such a complicated data set,
Yeah.
and they wanted to, do various things with the data from the peoples of Europe. But this guy, John November, let's just throw it all into the principal component analysis and see what happens. This is what happened. Absolutely amazing.
So there's just two PCAs, two principal components in this graph. They didn't do like PC3 or PC12, or do we also see that in this?
Well, I'm not going to show you those, but I think that might account for some additional variation not represented in this, but I think a lot of the remaining variation, even though the percent of variation actually accounted for by PC1 and PC2 is much greater than 1 over 200,000 each, but it's actually pretty small. But it's pretty much the only signal in the data, and everything else is just random. There's not much structure, geographical structure anyway, in the remaining axes. So I haven't shown it here. What the authors also showed is that the English and Swiss-German sections of Switzerland are also separated. So within even a tiny country like Europe, there's genetic structure from the two sides associated with language. So there's a lot of history and that gene flow in this graph. What they actually did is that they sampled people from all over the place and they asked them where their parents came from, I think is how they, because migration is just changing all this way. And it's gradually disintegrating. So that's principal component analysis, and that 200 by 200,000 data set, all we did was turn it and visualize it in 2 dimensions without really changing anything about the genetic distances between points. So I thought I would show you a couple of other analyses that you might also encounter. One of them is called discriminant analysis. So that was mentioned as well, discriminant function analysis. It might have been invented by Fisher, who, as far as I know, was the first to calculate a discriminant function analysis by hand, not even with a calculator. So the difference between discriminant analysis and principal component analysis is that principal component analysis treats every data point as a data point. There's no imposed structure on it. We just ask the data to tell us which the most variable directions are. But discriminant analysis, you already know what groups the data points belong to. And what you're asking the method to do then is to find a combination of traits that will allow you to maximally discriminate them. And so now we're not doing ordination anymore, we're doing classification. Often this would be used to classify new individuals. So here's an example of two groups, red and blue, and how they vary in 2 dimensions for 2 traits, 1 and 2. And if we ignored the colors and just threw the data points into a principal component analysis, well, here's the ellipse, which summarizes the variation and covariation in the data, and PC1 is the long axis of that ellipse. So that's what a principal component analysis would do if we gave it these data. And what we can see from this is that principal component analysis doesn't do a very good job of discriminating these 2 colors into 2 groups along a single axis. Discriminant analysis says we have 1 group here, we have 1 group here. And it explicitly looks for an axis that best separates the groups. Not just, it doesn't ask in what direction are they most variable. And the direction that most discriminates the 2 groups isn't the direction that separates the 2 means. You can see how much overlap there would be along that axis. When we look at the scatter of points, we can see that actually there's almost no overlap between those 2 clusters of points. And yet PC1 doesn't separate the 2 groups, and neither would the line connecting their means separate the 2 groups. The axis that best separates the 2 groups would be this one. So again, we're taking this scatter of points and we're turning it. And we're finding an axis such that when we look at it, if our eye is here now looking down, we can see that there's virtually no overlap in those 2 groups along that axis. And that's what discriminant analysis does. So it's kind of the same thing. And I would say it doesn't, I say the principal component analysis does nothing at all, it just turns. Discriminant analysis actually does stuff because it standardizes the axes in the search for this axis here, and so the distances between the points are all changed, they're all standardized. And so the units aren't the same as the original data.
Can I just quickly ask a question? What does it mean by relative to the thin group variation there, just to verify?
Yeah, so this axis here, you can see, separates those 2 groups, and it does so by virtue of the fact that relative to the magnitude of the difference between, so how should I say, we can see that the variation is high between these 2 groups along that axis, relative to the amount of variation along that axis within each of those groups. And so what the computations involve calculating all of the, you can imagine you could write a computer program that just does a blind search for the best axis. And along each axis it would calculate how different are the means between the 2 groups relative to the amount of variation within each group. And discriminant analysis would find the axis that maximizes that difference. That makes sense? It's easy to envision when there's only 2 groups, but now when there's 3, it's a little bit more complicated because with the 3rd group, only 2 of the groups might be separated. With the 3rd, yeah. So if you look at all the data points projected onto this axis, this is what it would look like. And now we can use this particular axis to decide how to place the new observation. If its value is 2, we would place it into this group with certain probability, and into that group with certain, in this case, very low probability. The point came up in the presentation and the discussion that isn't this just data dredging? Well, it is kind of data dredging, and especially when you have lots of variables. Discriminant analysis is very good at finding at least one combination of variables that does a pretty good job of separating the groups, and would do so even if the separation between the groups was not very great. So give it enough variables and you aren't data dredging. And so the way that people would handle that in a situation where they were trying to discriminate groups is that the discrimination would be conducted on a randomly sampled half of the individuals from this group and half of the individuals from this group. And then what I would be plotting is the histograms along that discriminant axis for the remaining half. And then we would be able to see how well this new axis works for observations that weren't actually involved in the identification of that axis. And that is how people would guard against essentially data dredging, finding a great axis based on just a slew of traits that was then not repeatable. We would basically be able to see how repeatable it was by using only half the data to create the axes, and then looking at how well, how good a job it does on the remaining half of the data. So if you do discriminant analysis, I'd recommend that strategy. One other method that we're going to try in the workshop this week is correspondence analysis. And it's an ordination method that's used a lot in ecological studies. It's a bit like principal component analysis. It's based not on the covariance matrix, but it's based on sort of a matrix of presence-absence data. And I'm going to show you kind of how it works using this ant data from Gattelli and Ellison. And we have 16 species of ants, and we have 4 sites. So those are think of those as the variables and the sites. And what we would like to, so a 1 means that the ant species is present at the site, and a 0 means it's not. And what we would like to do is to take this data and arrange it in such a way that we have somehow summarized most of the variation in presence-absence of species along a gradient of some kind. And a correspondence analysis would again allow you to look at the data in a small number of dimensions, in this case 2, and allow you to say, so ant species 5 and 12, they're right on top of one another, so they tend to occur at the same sites. And 2 and 4, species 2 and 4 tend to occur at the same sites. Whereas 14 occurs over there, and this group of 4 species tend to occur at the same site. And this first axis is not exactly corresponding to an environmental gradient, but it might. It's purely a mathematical gradient, but it might be real. It might be separating lowland from highland sites or drier sites from wetter sites. And thus these 2 species have similar ecological tolerances. And the sites are also plotted here to show that sites 4 and 1 tend to have the same ant species, whereas sites 4 and 3 tend to have very different ant species. So again, it allows us to visualize in a smaller number of dimensions than the original presence-absence matrix which ant species are similar. in terms of where they occur, and which sites are similar in terms of which ents are present.
Sorry, for that then, what do the axes represent on this figure?
So it's not really,
Is-
we're not really sure. And the next slide might help with answering that question, because what I've done is now I've taken all the ant species and kind of arranged them in a different order relative to their position along this first axis. And so they allow you to see that sites 1 and 4, I've also rearranged the sites along that same axis. And so you can see that, you know, the Vermont site and the Connecticut site tend to have the same ant species.
The axes are made up of the same things for both the
Correct.
sites.
Yeah, they're both made of the same. Ones and zeros are used to arrange. And sites 4 and 1 tend to lack the same species as well. Whereas 2, I don't know, site 2 is a little bit noisy. It shares something in common with Vermont and Connecticut, but then it has all these species and tends to be more similar to site 3. And these are 2 sites both from Maine, one in the, or I can't remember if that's Maine or Massachusetts. One from the islands and one from the mainlands. And so what is this axis? I don't know, but it's partly geographical and might therefore represent an environmental gradient of some kind.
So those axes can just represent, it's based off of almost the content of the data.
It's based on the content of the matrix, that's right. But more problematic is, what is the second axis? And that's actually much harder to... So it's not so serious in here, but in this example... Oh wait, let me just... Yeah, I think we finished looking at this. We do get eigenvalues, and they, in this case, they're kind of correlations. They tell you something about the magnitude of the association between species and sites along this first axis and along the second axis. So the particular method really tries to maximize the association between sites and species. And we see this correspondence in this, axis, or in this resorted matrix here. But the second axis is often difficult. And it's not so bad here, but often the data points are arranged in kind of a U shape. And I don't know if I have I don't really have an axis here, but you ask, well, what is shared along the second axis? What is shared between sites 3 and 4? We can go back to the matrix and go, what is shared between sites 3 and 4? Well, they have some species in common.
If some of the ant species occur in all 4 of the sites, is that adding redundancy?
If a species is present in all of the sites, or all 4 of the sites?
Yeah.
Yeah, where do they tend to fall? They tend to fall in the middle. A8, A9. And so the method really kind of pulls apart the extremes, tries to, it's almost like break them up into groups. Anyway, so that's kind of like principal component analysis based on presence-absence data, and you can do it also for distance data. And the last thing that I want to show you is that any kind of a matrix involving similarities or distances or presence-absence or population densities can be displayed in some kind of a space, an ordination. And I'm going to show that with my last data set here, which is from stickleback. And collaborators of ours sequenced 1,000 base pairs of a really important gene called ectodysplasin. So ectodysplasin is the gene that is mainly responsible for the reduction in the number of bony armor lateral plates. So whenever stickleback colonize fresh water, they tend to lose their bony armor. And EDA is one of is the major gene associated with that shift. And so, but there's variation in the non-coding regions of this EDA gene, and my collaborators sequenced 1,000 base pairs, and what this matrix is just different lake populations from BC, Washington, California, Alaska, and the number in this graph, or in this matrix, is just the genetic distance between the two sequences. So it's essentially a measure of the proportion of variable sites that are not shared, or the proportion of sites that are not shared. So along the diagonal is 0, every sequence is identical to itself. And each of these Cal2 and Cal3, they just represent different individuals. So this is just pairwise distances. And so then the question is, we have all these distances between all these pairwise observations. Can we represent that in essentially space? Can we place all those individuals in space so that individuals that are close together are genetically similar and individuals that are far apart are genetically very different? And if we can do that, then we can plot all of these data in just 2 dimensions. And that's essentially what the European human data did as well. And this graph shows that as for humans, as for stickleback, individuals that come from lakes in the same geographic region tend to be more similar in their sequence. And so we can tell sequences, we can tell alleles at this locus that come from Alaska, that come from California, or come from Washington and BC. And the methods that can be used to analyze these pairwise distance matrices are called multidimensional scaling. So you've probably heard the word before, but all of these methods share sort of one thing in common, and that is there's some kind of an association matrix, sites and species, pairwise distances or pairwise similarities or covariances, variances and covariances, and they can all be ordinated in such a way that allows you to see which points tend to be close to one another and which points tend to be distant. Next week is our last lecture and discussion. So I'm going to talk about, in my lecture I'm going to talk about phylogenies and how you analyze data when species are not independent. And the paper we're going to read is not exactly on that topic, but it's a paper about coming up, using phylogenies to come up with quantities that allows you to figure out which species are most unique and potentially of high conservation value. We have our presenters, we have our moderators, and you will be ready. So in the workshop this Thursday, we're going to try to run some of these multivariate analyses in R. And then I'll talk to the 4 of you about what's expected for the discussion next week, the presentation and the moderating next week. Okay? Let's give it time.
Okay.
Otherwise, we're running out.
So these are different, but yes. Exactly, that's okay.
So like,